So I work out a lot, probably more than most people you know. And a bunch of years ago, I was at the YMCA, and I love the YMCA. It's where I learned to swim, and I support their missions, etc. But I also have kids going to school and in college now, and I couldn't spend the money to be at the YMCA at the rates that they were charging back then. So I made a jump to LA Fitness, which is, and then they opened up a new one down the street a bunch of years ago. And they had a couple different programs, one of which was to spend $45 a month, but it cost $350 to sign up. Or you could spend $55 a month, and it only costs $250 to sign up. So, interesting. Which program would you buy? Which program would you buy into? Do you want to spend the more money up front, have a lower payment overall, or are you going to spend less money and have a higher payment? Let's see about this. So you've got your laptops open up. Hopefully you've got Google Sheets or Excel open up there. Let's actually put in a couple formulas here. So here's my two formulas. And let's see. Let's type in some numbers, like numbers of months. So I'm going to just title the top of this months, and then y equals 55 times t, or maybe I'll do it times m, because m is month, plus 250. And I'm just giving these some titles the same way I have it on our handout, plus 350. And I'm going to program in these number of months. So I got 1, 2, 3, etc. Now I get bored typing in all the months like this. So generally speaking, what I'll do is I'll type in equals this plus 1. What's the advantage of that? Can anyone suggest an advantage to doing it this way? Yeah, I can drag it down now. So I'm going to drag it all the way down to 13. So I got months totaling up to 1 year. Okay. Now you don't have to be fancy like that. You can type them in if you want. That's fine. What I want to know is I want to know how much money it's going to cost me overall, cumulatively, to be a member at these rates for however many months. So I'm going to program in these functions. Y equals 55 times number of months plus 250. And it says, do you want to do it all the way down? What do you think? Yeah, why not? Sure. Thank you. Appreciate you doing my work for me. We're going to do the same thing with the other column. So this one here. And this time my formula is y equals, equals 45 times the number of months, which is in column A, plus 350. Oops, that's 450. How about 350? Bam. And again, it says, do you want me to do this all the way down? Sure, why not? Appreciate it. And I'll just center those in both of my columns. Nice. So this is what we got. That's our number of months. This is our payments. I'm going to copy those down onto my handout here. But there's something that I want us to pay attention to. Maybe you'll run across it as you go through there. So are you able to get the number of months here? Are you able to get these numbers here? Yeah, yes, Izzy. All right. So let's take a look at that part down there. I need to bring this over here. I'm just going to copy these numbers down onto my sheet. So I got the first couple there for you, 360, then 415, then 470. 525, 580, 635, 635, 690, 745, 800, 855, and the last one should be what? 910 maybe? Yep, 910. Let me get that other column as well. So that other column is going to start out with the 395, the 440, and after that 485, 530, 575. And to get from one to the next, you're just adding 45. So there's a couple ways you could program this into Google Sheets. 620. What kind of growth is this, do you suspect? Is it exponential or linear? Linear. 755, 800, 845, and after that, 890 should be. Yeah, 890. Nice. Nice. Does anyone notice anything curious about these two columns? Remember, this is going to be the total cost after you've been in the program for however many months. That's an 890. Is there nothing about this that's kind of interesting or coincidental? Bryn?
I noticed that they both get to 800 at 10 months.
Yeah. At 10 months, it's kind of this break-even point. They both get to 800. So that's interesting. Now, if you were to graph it, the graphs would look like what you see up here. Which graph do you think is which? Which one, what color should I use for the top one? Orange or yellow? What are you thinking? Yellow? Okay. Why yellow? Yellow's right, she's right. But why should I use the yellow graph for the yellow color for the top one? What's that 250 or 350 represent in this problem? Does anyone know? That's your y-intercept, right? And the y-intercept for this one is higher than the y-intercept for this one, so it has to be this one right here. So I'll draw a little graph like this. And then I'll draw another one in orange for our other line. Try and land on it a little bit better this time. Now let's take Bryn's interesting observation that at 10 months, both of these graphs represented the same cost. How do you think that's reflected in our graphs? What do you think this point is reflected as on this graph? Perfect. The point where they cross. So at 10 months, both of these have the same price. So at 10 months, it doesn't matter which plan you pick. You will have spent $800 during those 10 months. Now, the question is, which plan would you want to be in? I mean, this is actually money. This is my money because I had to decide, well, which plan do I want to be in? Now, I guess which plan you want to be in depends on how long you're going to be in there, right? If you're going to be in there less than 10 months, which plan do you want to be in? The orange one or the yellow one? Orange one, because this line is less than this line. But after 10 months, now which plan do you want to be in? The yellow one. And the break-even point is at that 10 months. So fortunately, because I've been a member of LA Fitness for years, I took this one. Otherwise, I'd be spending a lot more money. It was a little more painful up front, but it's paid off in the long run. And that's what we're going to try and work on today, is solving these systems of equations. 2 equations and 2 unknowns. So that's what's called a system of equations. Our systems of equations are going to be really small. 2 equations and 2 unknowns. Although outside this classroom and in industry and stuff like that, they can get really, really, really big. But we're not going to worry about that here and now. Now, when you're working on these kinds of things, 3 different things can happen. You can get 2 lines that cross each other. That's great. If and where they cross each other, your system of equations is called consistent. You have a nice consistent system of equations. Let's take a look at this next pair of equations. We've got y equal x. That's this one right here. And then y equals negative 3/2 x. That's this one here. Which graph do you think I should, or which color do you think I should use for this downward sloping graph? Should I use pink or green?
Green.
Yeah, green. Green's going to have a negative slope. By the way, do these graphs represent direct variation or not? Yeah, because they're passing through the origin. You have linear graphs that pass through the origin, so this is direct variation. Is this system of equations consistent or inconsistent? Consistent would mean it has a solution. And the solution in this case is 0, 0. They both pass through 0, 0. So that's your solution. So that's the one thing that can happen, and we really like that one to happen. Because you've got a solution. We like solutions to our equations, our problems. But that's not the only thing that can happen. And I'll help you out with this one over here. I'm going to solve for y in both these equations. I want to get y by itself. So, let me think how I want to do it with this one. I'll move the 2y to the other side where it becomes positive, so I'll get 2y plus 3x equals 5. Then I'll move the 3x to the other side. 2y equals negative 3x plus 5. And finally, I'm going to divide everything by 2. And I'll get y equals negative 3/2 x plus 5/2. I can play that same game over here. I'll move the 3x to the other side and get 2y equals negative 3x plus 7. If I divide everything by 2, I get y equals negative 3/2 x plus 7/2. Now this is a little bit more than I would ask you to do for yourself, but I can graph these things now. And you can also get technology to help graph these things. This one in blue. Now the y-intercept here is less than the y-intercept here. So the smaller y-intercept has to be graphed here. That's this equation right there. By process of elimination, this has to be the other graph right here. Where do these cross each other? They don't. So if they don't cross each other, is there a solution? No. Well, when there's a solution, your system of equations is called consistent. What do you think you should call something if there's no solution? Inconsistent. Okay. So this is an inconsistent system of equations. This is the second thing that can happen, is you can have an inconsistent system of equations. So that's something else that can happen. Now, I'm not sure it's really going to be a big focus of this book here. But let me tell you about the third thing that can happen to a system of equations. and I'll do it this way. I'm going to graph this equation for you. It's y equals 5x plus 2 equals 6. You can graph this by plotting points. I'm not going to go into that now, but its graph would look like this right here. There's your line. And then you go and graph this one over here by again plotting points. And by plotting points, I mean one at a time. You set, for instance, x equal to 0. If I set x equal to 0, 5 times 0 is just 0. So I get 2y equals 6. Divide both sides by 2, I get y equals 3. I can then do the same thing for setting y equal to 0. 2 times 0 is 0, so this is really 5x plus 6 or 5x equals 6. Divide both sides by 5. 6 divided by 5 is 1.2. So you get that. So there's where those 2 points come from. Play connect the dots. Everyone's happy. If you played that same game over here, you would get exactly the same 2 points. And when you graph it, you're going to get exactly the same line. Now, I've done this really because these lines are one on top of the other. So this is the third thing that can happen when you're dealing with your system of equations. And the fancy word for this is dependent. I mean, that's great. It's a dependent system of equations. But these are the 3 things that can happen when you're working with a system of equations. You can have a consistent case, which is great. You can have an inconsistent case, which is kind of a bummer. And you can have a dependent case, which would be this last one, where the 2 lines are really the same. Can anyone see a way that I could go from here to here? What do I have to do to this equation to end up with this equation? Yeah, you multiply by -2. And multiplying by -2 doesn't really change the line. I've got different looking numbers, but it's still the same equation. So that's why you get one of these right on top of the other, and you end up with a dependent system. Okay, nice, nice. So there's a little background moving into our work here today. Let's apply that here. So we're going to work with systems of equations, and the example that starts off as a shipping manager at a small business sent out a shipment of 3 coffee mugs, 6 promotional packets on Monday, and the total shipping weight was 42 ounces. That sounds really light. I mean, that's what? That's not even 3 pounds for all this stuff, but whatever. We're not going to criticize that part of it. But we sent out all this stuff, and it weighed 42 ounces. On Wednesday, the manager sent 6 more mugs and 3 packets, so a different combination of stuff, and the total weight was 48 ounces. Then he thinks back, he's like, well, what was the shipping weight for each packet and each mug? That's the big question. So let's see if we can't write down a couple of equations here. And for this, we're going to assume a couple things. We're going to let X represent the weight of one mug, and Y is going to represent the weight of one packet. So we want to write an expression that, describes the combination of the weights of the 3 mugs and the 6 packets. Let's look back, because I didn't memorize those numbers. Maybe you did, maybe I didn't, but whatever. So let's look back here. It says 3 mugs and 6 packets had a total shipping weight of 42 ounces. Can someone write an equation that describes that part? Let me kind of highlight it here for us. 3 coffee mugs and 6 promotional packets. Had a total shipping weight of 42 ounces. What equation am I going to write there, assuming that X is the weight of the coffee mugs and Y is the weight of the packets? Who's got my back here?
3x plus 6y.
Good. 3x plus 6y. And what's that going to equal?
42 ounces.
42 ounces. Nice. Use your answer for question 2 to write an equation that describes the weight of the first shipment. Oh. I don't really see what they're looking for here. Use your answer for question 2 to write an equation that describes the weight of the first shipment. To me, it looks like I already did. That describes the weight of the first shipment. 3 mugs plus 6 packets was 42 ounces. So I'm just going to rewrite that again. 6y equals 42. But then they want you to repeat what we did here, except for the second shipment that was sent out. So let me highlight that. On Wednesday, the manager sent 6 mugs and 3 packets. And 3 packets for a total weight of 48 ounces. So try and use that bit to come up with yet another equation. If you came in late and you need to, please bust out Google Sheets. All right, 6 mugs, so 6x, and 3 more packets, total weight of 48 ounces. Jalen, what should I write there for my next equation here? 6x plus 3y equals 48. So between these two, we've got a system of equations. All right. Now our goal, when we have a system of equations, we can solve that system of equations for a particular variable or for both variables. We can try and see where they cross each other, like I did in my LA Fitness example to start with. Where do they cross each other? Where is that break-even point? So it says to solve each equation for y. Let's take a look at that. 3x plus 6y equals 42. If I want to get the y by itself, let me start by moving the 3x to the other side. What do I have to do to get rid of the 3x on the left-hand side? Subtract would probably be a better way to do it, but I appreciate the suggestion. Some of you said subtract. There's somebody says divide. Divide would kind of mess things up because I'd have 6x divided by negative 3y or 6y divided by 3x. If I subtract here, then I'm going to be left with what? Cora? Well, those cancel each other out, right?
Yeah, I was thinking you're from
6y.
30.
Well, these aren't like terms, so I'm just going to leave it as negative 3x plus 42. Say again?
No, I'm saying 42 minus 3x.
Okay, yeah, you can do 42 minus 3x.
Yeah.
I guess I'd leave it here because I'm accustomed to writing things as y equals mx plus b. So I tend to put the slope first. There's nothing wrong with what you're suggesting, that is, put it 42 minus 3x. Maybe it's more comfortable for you, that's fine. There's one last step I need to do to get y by itself. What is that last step here? So when you're looking at this, yeah, you ask, well, what's happening to the y? Y is being multiplied by 6. What's the opposite operation of multiplying by 6? Divide by 6. So we're going to divide everything through by 6. Divide by 6, divide by 6, divide by 6. And let's see what that gives us. So the 6's cancel. I'm left with y. How about 3 over 6? That's going to be leaving me with 1 over 2x. And 6 goes into 42 7 times. So that's my first equation. Why don't you try the same thing for the second equation? I'll let you work on that. So if you're watching this one later, then maybe pause things a little bit. Give yourself a chance to try this yourself. But try and do for this equation what we did for this equation. All right. So first things first, what should I do? Yeah. Subtract 6x. You can also think of it as adding negative 6x to both sides, but subtracting 6x is kind of the way I think of it. So thank you. So that's going to leave me with 3y equals negative 6x plus 48. Almost done. What's my last step? Skylar? Yeah, divide by 3. Notice everything gets divided by 3, even if it doesn't go in evenly like it did in the last one. Or like it didn't in the last one. So that's going to leave me with y equals what? Negative 2x plus 16. So that's my second equation. And so I got both of these equations now. I've got y equals negative 1/2 x plus 7, and y equals negative 2x plus 16. Let's plug in some numbers in here to figure these things out. Now, it's up to you. If you happen to have Google Sheets open, then you can open up a nice little sheet and make that do its work for you. If you don't, it's not that bad. Let's take a look here at 2 times negative 1/2 is going to be negative 1, plus 7 is going to give you 6. At 4, you end up with negative 1/2 of 4 is going to be negative 2, plus 7 is going to be 5. Can you see that? It looks like there's a little pattern forming already, right? If I do at 6, I end up with negative 3, plus 7 is going to be 4. Can we guess the remaining 2? 3 and 2. Now let's try it for this one as well. Here I get 2 times negative 2 is negative 4, plus 16 is going to be 12. At 4, I end up with negative 8, and 16 is going to be 8. And then at 6, I end up with 4, and then 0, and then, let's see, at 10 would be negative 4. Nice. Okay. Everyone okay with the table here? You could easily do that on Google Sheets, especially if you're at home. But I'm hoping that you can plug in these values pretty easily. There is a way to do it on your graphing calculator. I don't think many of us have a graphing calculator here today, so I'm not going to bother with that part of it. Let's graph these things. It asks us to graph both of them. We're going to graph them by plotting points. Now, just for ease of viewing, I'm going to graph this one in orange and this one in pink, so I can tell which one is which. But let's plot some points. Now, fortunately for us, this has already been plotted out for us. I mean, we've got the X and Y axes all set. So X was the number of, or the weight of a mug in ounces, and Y is the weight of a packet in ounces. Thank you. All right.
I don't have a 12, so I'm just going to put it up here.
What's that?
Because we didn't have a 12, so I just put it up there.
Okay. Yeah. Let's see. So first one was 2 and 6. Let's see. Do I want to do it that way? I'll do it here. 2 and 6, and then 4 and 5, and then 6 and 4, 8 and 3, 10 and 2. Now what's nice is that all these seem to lie on the same nice, neat, straight line. So I'll probably connect the dots through those. A lot of times I don't like to draw through the actual dots because then it discolors my markers. So if you're wondering why I'm skipping, that's the reason. What's that?
That makes perfect sense.
Okay. Let's take a look at the other one. We're having a little bit of a problem here with some of our graph, but that's okay. At 2, we start out at 12. So 2 is all the way up to 12. That's going to be up here. And then over at 4, we're at 8. At 6, we're at 4. And then 8, we're at 0. And we can kind of figure out what's going to happen at 10. 10, you'd be down here at negative 2. So probably about there, I'm guessing. Not that I necessarily think we need that point, but that's all right. You know, if I wanted that point graphed, I would have given you enough space. I'm assuming the same thing with the author. 4 and 8. 2. Why does that 4 and 8 look off? That's like really bothering me. 4 and 8, 2 and, oh wait, this would be 2 and 11, right?
You go up one more.
Yeah, I got to go up one more. I was looking at that going, wait a minute, these should all lie in the same straight line. That's why it was bothering me.
Literally said that this
Yeah,
was
you
as
did.
well.
You did, but I went through, I'm like, you know, wait, I just put it up there. No, 12 would be a little bit higher, right? 12 is actually off the graph accordingly. And so now I can play connect the dots. Now these are looking a little bit better. Because I was really bummed out about that one. I'm like, wait a minute, that shouldn't be off by that much. Okay. So we'll do this one. Oh, did I do these in the wrong color? I did. I think I mixed up the colors. Let's see. This one, no, this one should have been orange. Yep. All right, let me fix this. Yep. This one should have been in pink. I'll just fix that like this. What's the interesting point on this graph? Yeah, the intersection point, 6, 4. So that's the interesting point for us here. So lines look like they intersect at 6, 4. Plug in the coordinates of that point back into the original equations. What do you notice? Well, okay, we can do that. Actually, we've kind of already done it in here. When you plug in x equals 6, you get y equals 4. When you plug in x equals 6, you get y equals 4. So the thing that you should notice is that it works in both equations. If it works in both equations, then this is a solution. 6, 4 is a solution to the system of equations. Nice. Let's keep in mind that somehow or another this referred to the weights of a coffee mug and the weights of a packet. And the question is telling us, what does this tell us about the equations, or what does this tell us about the shipping weights of the items that we're working with? What information am I getting now that I got this 6 and 4? What does that tell me? How much does a mug weighs? Mug weighs 6 ounces. How about a packet? Four ounces. Nice. Morgan, question on that? A mug weighs 6 ounces and a packet weighs 4 ounces. Sorry about that. Nice, nice. Can I flip this? We good here? All right. How could you have found a solution from the system of table you made without graphing? Could we have found a solution from our table? Yeah. In fact, it's right here, right? In hindsight, we actually had our solution. It was 6 and 4 all along. That's okay. I think part of the point of this is that there's more than one way to solve these types of problems. Now, you know, you've got a test, I think a week from today. So I'm not sure I'm going to be letting you use Google Sheets for this stuff. But if I gave you a sheet like this and said to solve a system equation, Scott, then you'd be free to solve it like this, or you could solve it in other ways. And we'll explore some of those as we continue. But are we okay with where we're at right now? Good to go for our weights here. That's our solution, and that's a nice interpretation of our solution. Let's go a little further with this. So how could you have done this without graphing? Find the common point from the table. From the table. So our next goal is to start solving this a little bit more efficiently, and we're going to solve it algebraically. So rather than have to draw a graph or look at a table, I mean the table method could be a real pain, especially if those 2 points crossed each other at something that wasn't a nice even integer. I don't think most of us are going to be putting in crazy fractions into these types of expressions and looking at their XY pairs. It's just not the way we're going to roll on this kind of stuff. So it says, write the result you got earlier when you solve the second equation for y. If you look at it the right way, it provides another name for y. Let's actually write down both of these equations and our solutions for y. This is the second equation. So the second equation, when we solved it for y, was y equals negative 2x plus 16. In our first equation, we had y equals negative 1/2 x plus what, 7? That was our first equation. Thank you. If you look at this, we've got 2 different names for the variable y, right? So I could write y like this, or I could write y like this. Both of them are giving me the same thing. So what I'm going to do is I'm going to take this value of y, or this expression for y here, and I'm going to substitute it into this equation over here. And I'll get negative 2x plus 16 is equal to negative 1/2 x plus 7. How many variables do I have in this equation now? 1. I can solve this. If there's one unknown, typically speaking, I can solve these types of equations. This is a linear equation. Let's see if we can't solve this resulting equation for x. Now, in looking at this, is there something about this equation, some aspect of it, you're looking at it and go, I just hate these things. What is it? Come on, everyone knows what it is.
Fractions.
Fractions, yeah. Nobody likes fractions. They're maligned. No one likes them. So I've never really been a stickler on this stuff. My attitude is always, let's get rid of them. I can get rid of them if I multiply everything through by 2. Thank you. So now that means everything gets multiplied by 2. Not just the convenient part where we're going to get rid of the fraction here, but everything. So, Dejanette, when I distribute this 2, when I multiply everything by the 2, can you tell me what equation pops out of this? So 2 times negative 2x would be negative 4x plus 32. Good. Negative 1x. I'll just write negative x. I don't have to write the negative 1. If you're comfortable with it, you can write the negative 1. Plus 14. Nice. What's that? You know, if you want to do it with a fraction, power to you. My guess is if I did a survey, most people would rather not. Yeah, turn it to a decimal is fine. But if your fraction was 1/3 or 1/6 or 1/7, then you'd be less happy because those decimals aren't very, very pretty. Now, does anyone remember a suggestion I made a while ago? So, what side, Layla asked, should I put the variable on the left-hand side or the right-hand side? What was my little trick there? Anyone remember?
It'll be on the left hand, right? Largest number.
Put it on the side with the largest number. Now you might look at that and go, wait a minute, they're both negative. But still, one of these numbers is larger. Which one is larger, -4 or -1? -1. So you want to move the variable to the side with the largest coefficient. So I'll add 4x to both sides. What do I get when I add 4x to both sides? On the left-hand side, those cancel, right? 32 equals, not 4x, 3x plus 14. That looks a little bit more reasonable. All right, thank you. We'll subtract 14 from both sides now. So minus 14 minus 14. That's going to give me 18 equals 3x. Divide by 3, and what do I end up with? 6. Wow. That's the same thing we got earlier, right? Now, if you wanted the y variable, and typically speaking, you will, you'd plug that back into one of these two expressions. This one looks better than the other one, but it doesn't really matter. You plug it back in, and you get your y equals 4 from substitution. So, yay. And in fact, that's what we call this method, is the method of substitution. It's one of the ways you have that you can solve a system of equations. Nice. Nice. Let's keep going. We're going to work on a brand new example here. So before I finish up with this, are we okay with some of the things we've done? Maybe we'll take kind of a quick look back and review this. So initially, we had a problem that described something in a couple different ways. We had 3 mugs and 6 promotional packets, total up to 42 ounces, and then another combination, 6 and 3, total up to 48 ounces. That gave us 2 equations, this one and this one, that we then solved together. We had a system of equations right here. Now, initially we solved it by getting y by itself in each of those equations and plotting a table. We noticed that those 2 lines crossed each other at one point, and that one point was our solution. So there's really 2 different ways you can solve it embodied right here. One is with a table. That was our solution there, 6 and 4, 6 and 4. Or seeing where the graphs cross each other. Now both of these are a little bit hit and miss. They're working because these are nice equations with integer solutions. The way we're going to have to work on these things more generally is we're going to take these 2 systems of equations together and then solve them. So that was the algebra work we did to finish solving those. And let's see where it lost it here already. Okay. Yeah, that's this part right here. We actually solve these by the method of substitution. And that's a little bit more general, more efficient way to solve these systems of equations. Okay, so let's pick it up with, let's see, is that the bottom one of these? Yeah, bottom here. So starting down here, a brand new system of equations to deal with. While traveling on business, Eldrick bought $50 in prepaid phone cards to call home. Calls cost $7 per minute. how many minutes has he used if his display shows $32.15 remaining. Okay. So that's all the basic info here. Let's put this together and see if we can't find a couple things. Some of the things that I think we're going to want to keep in mind this $32.15, and that calls cost 7 cents per minute. We have $50 on the card to begin with. Okay. Backside. We're going to have to write two different equations. One of them states that the value on our phone card is $32.15. All right, that's a pretty simple one. What does the word is translate to mathematically? What symbol can I use for the word is? Equals. So the first one is pretty easy. V equals 32.15. So that's one expression here. Let's work with the other expression. And for that, I want to write the equation that represents the value of this card right at the start. How much is that card worth at the start? $50. And then it costs us 7 cents for each minute that we use, and each minute is X. So minus, is that enough just to write 0.07? No, because now you're subtracting 7 cents. You need to subtract 7 cents per minute. So that would be 50 minus 0.07 X. Okay. So let's take a look at what happens to the value of his card after so many minutes. Now, being very helpful, as I am, I'm going to take our first equation and solve it down here for all these different values of X. So when X is 0, that's 32.15. When X is 100, this is still 32.15 and 32.15. As you can see, I'm not being actually all that helpful, right? 32.15 all the way down. This is a constant function. It's just a flat, straight line. Where you're going to have to actually do some work is with this card. When you haven't used any minutes, you've got $50 left. Can anyone multiply, say, 100 times 0.07? What's going to happen there? Without your calculator. 100 times 0.07 is just going to move the decimal, right? What are we going to get? A die? 7. And 50 minus 7 is going to be 43. If we go another 100 minutes, now we're spending another $7. So how much would be left after 200 minutes? 36. Let's keep going. Taya? Spend another $7. So we'll use another 100 minutes. Now how much is left? Yeah, 29, 22, 15. Did I find the actual point where these two lines cross each other? But where is it between? What do we know it's got to be close to what values someplace? Yeah, somewhere between 200 and 300 minutes, right? Around 200 or 300 minutes, you're somewhere in there. You're going to cross that barrier for 32 minutes and 15 seconds. All right. Let's graph both of these. So this is your X, this is your Y, and then you have another pair of X and Y's, X and Y for the second equation. For the first equation, 32.15, it's going to be somewhere, let's see, that'd be 35, so 3215. I'm going to put it about here, 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 here. So 3215 all the way across. So it's just a nice horizontal line. How about the next one? Let's see, we've got 0 and 50. That one's pretty easy. 143, 45, yeah, about there someplace, 143. 236, so that's going to be a little bit north of our line. 329. 422, and last but not least, 550, or 15, I should say. So that's our other pairs of points. Use your graph to try and estimate the solution. So take a look at your graph and see if you can figure out roughly where the solution is. What coordinates would it have? Okay, let me hear a couple estimates. What are you estimating this solution to be? Amadou, want to give that a shot? What would you guess it is? Give me a number. Just throw out a number.
250.
All right, so 250. All right. What else we got? Is it 237? All right, cool. Anyone else want to throw one in? 245. All right, good. It's kind of tough to tell. I mean, we're looking at these, and we know it's someplace between 200 and 300. But even the graph doesn't give us a great idea of where that is. I don't know. My graph makes it look exactly like 250. I'm not sure that it is. So the question is, do you think we have the exact answer here someplace? Yeah, maybe not. Maybe not. I don't know. But would you be confident that we had the exact right answer? Yeah, I wouldn't be brimming with confidence either. So, not very, because it's an estimate. And what's happening is this is really showing you why you need to be able to do something better than just fill out tables or look at graphs to solve your system equations, because sometimes you can't do it directly off the graph or table. Sometimes you really need to spend some time with, for instance, the method of substitution. So if I wanted to actually solve this system of equations and find out exactly where they cross each other, what would you suggest I do? Yeah, set them equal to each other. We're going to use the substitution method. So that's this part right here, substitution method. Scott, what equation am I going to get for this if I use the substitution method?
32.15 equals 50 minus 0.17.
Nice, thank you, sir. Let's see. Cardell, what would you do to start solving this one? There's a couple different ways you can go. What interests you? What works good for you?
Minus 50.
All right, we'll subtract 50 from both sides. On the right-hand side, Emma, what's left?
You have negatives. Oh, on the right-hand side? I'm sorry. You just have negative 0.07x.
Yeah, negative 0.07x. On the left-hand side, you're going to have what? 17.85? Negative 17.85. Looking better. Marley, what should we finish up with, please?
Dividing by negative 0.47.
Good. So 17.85 divided by negative 0.07 equals x. Now, when you do this on your calculator, save yourself a little step. What happens when you divide a negative by a negative? Positive. So, all right, we expect a positive number. It makes sense to get a positive number. In fact, we expect something between, around 250. But yeah, you can skip out on the worry about the negatives. You know it's going to be positive, so we'll just skip that. 1785 divided by 0.07, 255. Yay, so 255 equals x. How would you determine the second coordinate of our solution? Because remember, our solution has an x and a y coordinate. In our case, it's going to be number of minutes and the value left on the card. How am I going to find that value? How could I find that value?
Input 255 is x and then solve for y.
Yeah, you can take that 255 for x and plug it in to solve for y. Let's see. So we could definitely do that. Is there an easier way I could figure out what v is? Maybe right here in this equation, right? V is 32.15. You get the same thing either way, but your V in this case is 32.15. So the overall solution, and please keep in mind that on an exam, if I'm asking for you to solve, I want an X and a Y. I need an X and a Y to get a complete solution. I mean, you get most of the credit if you had to solve here like that, but overall the solution should be 255 and 32.15. Good with that? Was there a question, Cora? Did you have a question?
No.
Okay.
We're backwards.
Oh, okay. Yeah, I mean, sometimes that happens. I get it. Beautiful. Beautiful.
I tend to write things out of order, so I end up writing middle of numbers, then
Okay.
outside of them.
Any other follow-up on this one? So this is kind of nudging you to the direction that, yeah, sometimes we need to be able to solve these types of equations directly using algebra. So solving a system of equations, and that's about as complicated as that we're going to make these for this course. I'm not going to go much beyond that. So last chance, anything else? Look good? Okay. Let's shut this one down for today.